Да, привет.
Hey, good morning, fellow nerds. Welcome to another episode of Between Two Nerds. I'm Jeff Doyle, and uh, on the phone there is my friend and partner in crime, Jeff Tansura. And looks like we've just lost Jeff. We're still waiting for our guest, Dmitry, to join, and we're going to kind of fill the time until he joins, I believe. And our topic for today. Sorry, we're sort of had a last minute strangeness here. Our topic for today is scaling in the data center, and I think that's a topic that's going to carry us through multiple episodes. We have a long list of topics to talk about, and let's see, Jeff, are you back? There you are.
Hi, good morning.
I was babbling there for a second while you were
So
on.
5 minutes delay. Sorry, some technical
5 minutes
difficulty.
delay. Okay, well, we're live right now, so we'll just chat over those 5
Yep.
minutes. What I was starting to talk about is that our topic that's probably going to carry us through multiple episodes is talking about scaling in the data center. As you may have seen, those of you that are watching may have seen that advertised as our topic, and there is a tremendous amount of material we can cover on scaling issues. And Jeff, do you have can you sort of give us an overview of scaling as far as challenges in a data center?
Yeah, so we are going to be joined by old friend of mine and one of leading network engineer architects at Yandex, which is a company with similar business as Google in the rest of the world, but in Russia. And they've got their hyperscaler. We got large network, significant number of data centers, and the scaling issues they experience, they're similar to any other hyperscaler with regards to management, with regards to how to build out, how to make sure that failure domains are limited.
Mhm.
And they've been pretty advanced in technology, tried to use. They were one of the first hyperscalers to try MPLS and data center. So they actually drove an effort known as LARP or labor ARP. There's a draft in ATF that Kirati Compiler is driving to receive label through ARP request. Right, it's an interesting idea, but if you're end-to-end MPLS, you actually need to be able to get label or binding of IP address to label value before you can send any traffic. Hey, Dima.
Can you hear?
Hi, Dmitry. Yeah, your volume is a little bit low there.
Yeah.
I barely can hear you.
It's pretty low.
Can you hear me? Any sound?
Yes, we can hear you. You could talk louder or perhaps sit closer or to the mic.
And is sound level enough or not? Because it's really quiet for me.
It's reasonably okay on your side if you keep talk louder.
Okay, I figured out why it's quiet, because it seems that it's not picking earpiece. Just a moment. Maybe it's better like that.
So we'll continue with introduction while Dima is fixing his technical issues. So there's significant number of topics to discuss. from basic why are we using leaf spine networks to how to design routing around it, issues that are to be solved if we are trying to build something more interesting, more advanced. And we spend a lot of time with Tony P on Rift. So Dima is one of Rift co-authors. He contributed extensively to developing Rift specs and actually did some testing. So we'll come to some discussion about Rift as well.
Great.
So Dima, how are you doing on technical stuff?
Doing
Can you
fine,
hear us?
and that now I can hear you, and hopefully sound is fine on your side as well.
Try
Yeah,
to sit a bit closer to the mic. It's
Huh?
still a bit on low end.
Okay, let's try it. I can move it actually.
No, to the mic, not to the camera.
Unfortunately, they're sort of coupled.
Okay.
oh, actually, it sounds better now.
Yeah. Let's keep it this way.
So just a moment, yeah.
You still have a Christmas tree. It's funny.
Yeah, it's actually still more or less green and still smells like a Christmas tree, so I'm keeping it for a while.
Till May, right? Okay, so we've introduced yourself, but you could go ahead and tell our audience a few words about yourself. Where are you? What drives you? What's interesting? And I know you've got some slides. You could try to project them. If it doesn't work, we'll just talk through.
Yeah, so, well, I'm a network architect working for Yandex. Yandex is essentially it's Russian Google, mostly Russian. For a while, it was mostly operating in Russia and former Soviet Union countries, but now it's expanding, especially with some projects, because historically it was mostly search, then network storage, email, all the usual set of services, a lot of machine learning stuff recently, and also self-driving cars, and not only cars, but those small bots, delivery bots, and public cloud. And with those projects, Yandex is also expanding beyond the traditional markets. So we have self-driving car people in United States. We have some projects in Europe, and so on and so on. We are operating more globally in recent years. And in terms of infrastructure, yeah, we're typical hyperscaler, albeit on a smaller size. I mean, we are not Google or Amazon size, but we are big enough to have a similar set of problems. And mostly we are looking at similar solutions. But of course, there are options. So we are doing similar things, we are solving similar problems, but not always exactly the same way. So I have a bunch of slides for today. I will try to join from another device to show them. But I'm not going to strictly follow them, but mostly like discuss around them. And briefly, what I want to do to talk about is like how we types of workloads, what we're looking for in terms of metrics, how we build our data center networks. Like we are building typical Clos networks. It's Clos or maybe Core because Charles Clos was French, so it's probably without S. How just a small recap how to build Clos network recursively. Because a very nice feature of Clos is that you can build it recursively and grow it as large as you want, essentially. Also look at how we do routing, addressing, what are limitations. And after that, to talk about what's next, what interesting things we can do beyond Clos, what I'm looking at. what we cannot do with modern hardware, because, for example, some analytics or monitoring is not easy to implement, and we have to use some indirect methods. And that's a sort of answer the question, what drives me. What's interesting for me is basically to solve scaling problems, to look beyond what we are doing now, because we mostly know how to solve problems with closed networks, how to build them to a reasonable size, where reasonable is constrained by software infrastructure and power. So basically, we are at the moment targeting something about 100K endpoints. We define that as large data center we want to be able to build. We probably don't want to go beyond that because we are becoming power limited. 100K nodes, it's on the order of 50 megawatts, and that's basically how much power we can get in single place. Beyond that, it's probably not a single data center, but like data center campus, or even more regionally spread data centers like availability zone, but not a single place. But in terms of topologies, advanced routing, we are definitely looking at what's possible to do beyond Clos, and that means non-shortest path networks like Dragonfly Plus, and maybe even more fancy topologies. Another interesting direction is networks, or some people call them interconnects, for distributed machine learning applications. And that's where traditional networking sort of intersects with in-network compute. Like people want to talk about in-network compute, but essentially like 99% of in-network compute, which is interesting right now, is doing some part of collective operations in the network. Traditional APC collective operation in network devices. And usually it's not something difficult computationally, but if you are doing it in the right place, you can improve performance, reduce traffic, and do some nice things. And another thing we are working and doing some R&D internally is one of the things. We are doing a lot of things, and I'm involved in only some of them, obviously. But another area of R&D is congestion control, of course, because there are a lot of improvements which can be done there, and in data center, traditional, which is mostly deployed in Linux kernel, for example, congestion control is not so good. And congestion control based on loss metrics is not so good, and reaction times and fairness. Basically, it's possible to do better, and some other signals like ECN in controlled environment and RTT and latency could be used. So we're experimenting with different kinds of congestion control.
So
it would be nice to have some universal one, but currently what we see is that in DCN, in wider network, and especially for connection going beyond our infrastructure, probably you have to use different kinds of congestion.
Yeah. So as you could see, there's enough material probably to 2-3 podcasts, which we definitely plan to have. And everything that Dima has discussed is not unique to Yandex. All those discussions happening at Microsoft, Amazon, Google, and any other hyperscaler. Discussion about how to interconnect 10,000 GPUs without dropping any single packet. I mean, it's something kind of happening on a daily basis, right? How do we do it? I mean, traditionally, a lot of people did InfiniBand, but it has its limitations, both technology and business related. So I think there's really big push to try to align with more regular compute rather than trying to build snowflakes. So we are going to come back on a lot of these topics with different people, provide their view, some solutions, some work that's going on in ATF and IRTF. And Dima, please go ahead, and all yours.
Yeah. So give me a minute. I will try to join from my computer to share slides.
And just for the sake of not having dead air here, Jeff, while Dmitry is getting his slides up, can you give us kind of an intro on where we want to start? I mean, we've gone 15 minutes now, talking about and pretty much emphasizing, that this is a massive topic in scaling, and so where's the right place to start when we're addressing this? Because right now,
I think we should start with the start, right? So what have we been doing over the last 5-7 years? What's running today, and what led to this kind of topologies, routing domains, and why did we do it? So we really start with the start, where we are today and why we are there, right? So Dima is going to go in details into why we use Clos today, and how we get there, and eventually we'll get to more advanced topics.
Okay, so yeah, I mean, for the folks watching, if you're not familiar with the basics and ins and outs of Clos architecture, I'd say you probably haven't been watching the show very much, because there's not many shows where we don't say something about Clos, right?
Yeah. So could you repeat, please? I probably missed the last half minute or something.
Yeah, no worries. We were just Jeff and I were just kind of chatting here about where to start. There's such a massive topic talking about data center scaling, and where's the right place to start in the discussion. It looks like just an enormous landscape of topics here, and I think what I'm looking at is how do we dive into a specific starting place. Hey, there we are. There's our slides.
Yeah. Those are slides, and well.
Perfect. We'll get your slides up. We'll just hand it over to you, Dmitry.
Yep.
Yes, probably I will continue. Just a disclaimer, I definitely not planning to fit everything in today's podcast, but I will try to go through as much material as I can, and will try to answer questions, but it's definitely a topic not for a single podcast episode and much more. So I don't think I need to discuss too much about what hyperscale computing and data center as a computer, but basically it's not only big infrastructure, but it's also ability to dynamically scale it, and also to build it quickly enough if you have rising demand, and do it without stopping or interfering with operations. And another thing is, it's definitely data center as a computer. We consider it, we don't talk about single nodes usually. We are talking about distributed applications running in the data centers, and some data center scale operating systems, including workload placements and so on. And that brings us to what large data center means for us, for example, because packet scale and packet size, how many endpoints we are talking about, not only limited by how we can design a network, but also by how much power we can get in a single place, and also how scalable that data center scale operating system. We are targeting about 100K nodes at the moment because that's what our scheduling and workload placement components can do. They scale to approximately that size, maybe a little bit more, but those things are aligned. It doesn't make much sense to build data center much larger if software components cannot address it. And another thing is, before we are talking about infrastructure, and to figure out what metrics we consider important and what metrics we consider not so important. So in large-scale environments, we are mostly looking at statistical metrics and distributions. So we are talking about flow completion times and percentiles, tail latency, also about statistical service level objectives like availability of some service or some component with performance guarantees for this amount of time, essentially. What is less important is averages. Percentiles and like tail latency is much more important than average things, because if you are looking at some historical metrics for our data centers, for example, average load is not that high. It looks like infrastructure is almost underutilized. But if we reduce bandwidth, for example, significantly, it seems to be enough to satisfy average bandwidth, but those peak loads and tail latencies start to grow. So it's really important to look at statistical things, not averages. And also, we are less concerned about efficient capacity utilization if we are talking about network capacity utilization in the data center, because less efficient capacity utilization in the data center is what allows to more efficiently utilize compute and storage. Essentially, we have to over-provision network a little bit to be able to place workload wherever we want to do efficient resource pooling. And at the moment, at least, compute costs are much more than network costs for us. Also, since it's a really big infrastructure, we are not looking so much as the reliability of single elements. They come and go, both endpoints and network devices. So it's not a question how to figure out where to how to build most reliable elements or where to get them. It's how to build infrastructure which can tolerate and work normally when elements come and join it, and sometimes go out. It's normal. When you have thousands of network devices and tens of thousands of endpoints, on-off events are essentially a normal part of life. And since we are talking about networks, there are some very good books discussing interconnection networks and discussing topologies. It's both historically and now, essentially, there are only two kinds of network topologies. Those are direct topologies, where the same elements are used for transit traffic and as sources and sink of traffic, and indirect, where we have dedicated elements which are only doing transit. And factory or closed networks are indirect, and some things like Torus, Mesh, Hypercube, historically used in HPC environments, are direct. I wasn't there because a lot of things happened like before I started to do interesting things in networking, but if I understand correctly, transition between mostly direct networks with high bandwidth, what was traditionally used in HPC, to what we have now with a lot of factory, close, and maybe things like Dragonfly, happened because of two things. First, really high performance, high Radix switches became available, and also optics became cheap. I mean, optics which can go beyond like dozens of meters, 100 feet. Because before that, there was a very strong motivation to build really compact things, because once you go beyond the lengths where you can do cheap links, infrastructure, network infrastructure becomes much more expensive. But just to remind, we still use, I mean, not we as Yandex, but we as an industry still use direct interconnection networks, especially in some specialized applications like distributed machine learning training, because, for example, Google TPU clusters, it's using like 2D torus still. And there are reasons for that. We can talk about where direct networks and those unusual for traditional networking topologies make sense and why they make sense. But we are building indirect networks and tree-close topologies. If you're talking about large data centers and general purpose networks, essentially there are no real alternatives at the moment. And fat tree-close networks, they are good enough if you have high Radix switches. If you're talking about our infrastructure, it's layer 3 only, because layer 2 doesn't really scale and it doesn't mix very well with multipass environment. And if people really want to do layer 2, it's always possible to do it in overlay. But for Yandex, for example, there are actually two kinds of environment. What we were doing historically, it's like search and essentially our internal distributed applications where we control entire stack from hardware all the way up to software, libraries, and applications. And we are using container-based virtualization for that, mostly for resource control. We control our own applications, and most of those applications, they're distributed from the start. They operate on dozens, hundreds, thousands of nodes. They can handle failures. They just don't need layer 2. And another environment, also in Yandex, is public cloud. And they're using overlays. So if they want to do some fancy things, they're doing that in overlay. Just a small recap of what is multi-stage Clos and how to build it, and how we call different things. For us, the lowest level, level 0, it's either leaf or top of the rack switch. Then we have next layer, which is spine 1. We call it spine 1, and then next is spine 2. Leaf switches and associated spine 1 switches comprise a single building block of the networks, which is pod, and spine 1 switches of single pod, it's top of pod. It's the same terminology which is used in Rift draft, actually. And the topmost layer of switches is top of fabric. And when we discuss traffic patterns and where links go, it's very useful to talk about east-west or north-south directions. Also, like what I have in the picture is sort of canonical folded clause, no additional links and so on. People sometimes try to add horizontal links or some extra connectivity where essentially what you have between level 0, top of the rack switches, and spine 1 switches. Some of connectivity is repeated on the next level. I don't think it's really necessary because it's essentially a waste of Radix. If you can do those additional sideway links, that means you probably can build larger and wider network without them. Before we go further, building closed networks for many years now. And can we do better than that? Yes, theoretically we can, and there is a lot of research. There are a lot of interesting topologies, but it's not really feasible now for general purpose networks because first we need a new control plane, because all those interesting topologies, most of the capacity lays along non-shortest path. So we would need control plane or centralized controller which can discover those not shortest path. And then we need a forwarding plane where we could install those non-shortest paths. Also, that means we should be able to make non-shortest path forwarding decisions, and probably that means also source routing and all-at-once forwarding. That means using some additional encapsulation and doing things like, for example, segment routing in the data center, which is a very interesting option, but not really feasible right at the moment. And also for those interesting advanced topology, we really would need adaptive routing, because when you have a lot of paths which are not the same length, we would like, under light load, we would like to really use a few shortest paths because that just makes sense. It's they're shorter, they're low latency. But once we have more load, that means we want to offload extra traffic to longer paths. And that means we need adaptive routing based on some parameters like local queue utilization. And not only that, we also need some to really get all the advantages of those topology. We also need global adaptive routing, and that means some feedback. When we route traffic along some non-shortest paths, we should be able to get feedback beyond single hop. It's not really feasible to sample really fast the global state of all the queues in the network, and that means we need some sort of selective feedback, like adaptive routing notifications or something like that. So alternative topologies is a really interesting topic. A lot of R&D done, and they're really used in HPC environment. And recently, for example, Slingshot Interconnect from Cray, they're using the switching elements. They're essentially based on some Ethernet switch, highly modified, but still Ethernet switch. So it's possible to introduce a lot of the necessary functions into the Ethernet IP environment, but it's not going to be our standard Ethernet IP environment. So it's not something which is possible to do right now for general purpose network like today, but it's definitely something we would like to be able to do in midterm, at least try to do.
So there's some work that's going on enhanced congestion control. There's some work we at Max have been doing with our colleagues from Alibaba, work called High Performance Congestion Control HPCC. There is related paper at SIGCOMM and draft in IETF where we are describing how it's working. The idea is to use in-band telemetry to provide this data at single RTT back to the sender. Sender in this case could reduce its transmit rate or change entropy. So change, for example, destination UDP port in the traffic. So potentially traffic would take another path. So there's some work going on. We are still kind of in the design phases of this, and we'll keep you updating probably in a month or two when we publish updated draft. I'll invite my co-authors and we will describe what we're trying to do.
You mentioned really important things that in those kinds of topologies, and actually even in factory in Clos for some workloads, it's really useful to have feedback, fast feedback on the order of single RTT time. There are different ways to do that, but it is really essential to have good performance. So going back to closed networks, since currently we are building closed networks, how we can scale them? Size, or essentially width of closed networks, is product of south radix of all the spine layers. So that means there are different ways to scale it. It's possible to use high radix switches. It's possible to add more spine levels, and size of closed networks grows really fast with adding additional layers. Another scaling parameter is the capacity per leaf switch, and that scales as the number of planes where it's connected, and of course with the bandwidth of single link speed. And that means that industry basically every few years delivers us more bandwidth for the same topology, for the same structure of the network. But if we want to go beyond that, we need to either add more uplinks and planes in the closed networks. Well, for leaf switches, it's just that. It's high-speed links or more planes. But adding spine levels is very good way to scale closed networks. Problem is it's not cheap way, because each time we add in one more level, we essentially need to replicate all the bandwidth on the previous layer on that one, if you don't want to introduce oversubscription. And for capacity planning reasons, to simplify it, usually we try to do oversubscription only at single level at the moment, but we are doing some R&D regarding capacity planning and modeling. So hopefully we will be able to have more tight bounds on our subscription levels and do our subscription at both, for example, leaf switches and between spine 1 and spine 2. But it's not an easy task, because events of concern is something like incast, and those events, they're really fast. So traditional monitoring and streaming telemetry on the switches don't have enough resolution in time to capture the event. And we either can do some modeling, or we can try to derive the shape of that event from some indirect metrics, but we cannot really observe it and from real traffic on real network. There's no way to capture that. If you don't know in advance, of course, when it's going to happen, and in reality, we don't know in advance. In strictly controlled experiments, it's of course possible to capture the shape of that pulse and surge in traffic, but in production, we usually have some indirect metrics like packet loss, or maybe how many packets were missing in the market, whatever, but we don't capture the entire event. And getting more information about those transient and fast events would really help with capacity planning. Going back to scaling, as I said, it's possible to add more levels, or it's possible to use high radix switches. And currently, the pictures there, I try to show both ways. We can start with basic elements in the upper left corner, the very simple two-layer closed network. We can use high radix switches, and it's shown to the right of it. We can add more levels. That's in the lower left corner. And we can combine that, and it's easy to see that combining both, we can very quickly increase the size of the network. Just some numbers, how quickly the size of a possible network grows, and also how much bandwidth is usable, because when we add levels, we spend some capacity, some bandwidth on inter-switch links, which don't add useful capacity to the endpoints. So with only one spine level, we are have 1/3 of bandwidth usable for endpoints. But scaling is not so good. With 2 spine levels, if switch Radix is 32, for example, which was available, I guess it's 8 years ago, maybe little less, those were like based on matched silicon switches, not so bad, but it's still, with 2 spine layers, it was only possible to go to 512 racks. Still not the size we want, but if you are talking about 64, 128 Radix switches, it's easy to see that we can go to 2K, maybe 8K racks, and that means all the way from 40 to 160 megawatts. So that's about a real size of the data center we can build. Everything beyond that, like 2 spine levels, but more than 120 Radix switches, or 3 spine levels and beyond, it's sort of theoretically interesting, but we cannot get that much power in a single place to build those kinds of networks. So in our designs, we are targeting closed networks with three tiers, 3 levels, 2 of them spine levels, and we really want to use 128 Radix switches, whatever the link speed, because the number of elements depends on Radix, and sometimes it's better to go with a little bit slower links, but high Radix to be able to feed them in just 2 spine levels. Because if you want more capacity per leaf, we can just add more planes in the network without increasing the number of levels. But if you don't have enough Radix, the only way to go is to add next level, and that means we are repeating bandwidth once again. It's really important consideration, because if you are making just adding planes, we are not wasting bandwidth. We are not repeating bandwidth one more time. Because the usable bandwidth within each plane is the same. But if you cannot feed the network because of Radix and need to add one more level, that means repeating bandwidth once again and wasting more bandwidth. So definitely better to keep height or number of levels in the network lower. And 1 level is obviously not enough. But for reasonably sized networks, we can go with 2 spine levels now because of availability of high Radix switches. It wasn't possible to do that 5-6 years ago, probably, but or maybe possible with doing things like breakout cables. Not a nice thing, especially if you need to do a lot of cabling. But right now it's possible, and it looks like 2 spine levels, high Radix switches is going to be sort of standardized design, at least.
So I would like us to pause here and expand a bit on why high Radix is so important.
Yeah.
Ideally, we would like to keep all connectivity on the single chip, right? Because if you look at clock structure, there is no horizontal links. So if you aren't keeping everything on single switch or single piece of silicon, you would need to go to higher level to come back, which is 1/3 of capacity. Most importantly, it's very expensive from electricity perspective and cooling, right? So it requires optical links. So that's why when we get to 400 switches, in most cases, we would actually split it into 4 times 100 gig, which brings another consideration here. So usually number of MUX or your split is equal to number of SerDes. So SerDes is an internal component of a switch, which is serializer, deserializer. And today we mostly see 50 gig SerDes with 100 gig already available. In other words, if you have a 400 gig switch, today you can buy probably 32 times 400 gig of the shelf. If it uses 100 gig SerDes, you will get 4 MUX per 400 gig, meaning you can split it into 4, but no more. If you get 50 gig SerDes, so in both cases PAM4, suddenly you could get up to 4 times as many MACs. So you always need to think how you are going to split. And there've been a lot of studying around, should I go fatter links or by Radix? And as Dima said, why the Radix always wins. It provides better load sharing. It provides more or more efficient connectivity, because everything is on the same silicon, so you don't need to go up to come down. It provides better resiliency, because now you've got more links, and if you lose one link, you actually lose just 1/8 or 1/16 of capacity rather than 1/4. So there are many reasons to look into wider Radix than faster links.
Yeah, totally agree. And I even have a couple of slides about why we want to use single chip devices. And a lot of arguments are the same. And I also would like to mention that when we are talking about devices which are not single chip, what we usually can find inside the device is that it's essentially in mini Clos inside the package. Mm-hmm. So we prefer to make it explicit, like with all the links external, rather than being packaged inside the device, because single chip devices, they have much simpler failure modes. They usually fail entirely, or maybe single port fail, but they don't fail in fancy ways like forwarding table wasn't synchronized between components, or some internal links failed, so now it's sort of full capacity but not in all directions, and so on. Complex like multi-chip devices have really nasty, rare but nasty failure modes, which are difficult to debug, difficult to troubleshoot, and even the amount of quality of tools to troubleshoot is not so good, because when all your connectivity is like Ethernet links, you can do traffic capture, you usually have some decent amount of counters and so on. When we are talking about fabric links inside the device, first of all, sometimes it's even difficult to get a proper documentation, what counters are available, what statistics is available, and so on. And tools to troubleshoot and monitor it cannot be really compared to what we have on proper Ethernet links.
So usually when we kind of trying to consider whether to use single silicon system versus a chassis, they should be much more than just kind of packaging. Think about deep buffering. If you use something like InfiniBand or Rocky V2, sometimes buffering is absolutely necessary. Many chassis system provides technology called VOQs, meaning they allow you to separate traffic per priority or some other classes, and they guarantee delivery of this traffic within its priority across switch fabric, right? So if you take classical chassis router, they all utilize VOQs, right? Yeah. So usually it's not just number of line cards you can put, but all the additional stuff that you get on top of it, being additional buffering memory. For example, if you build today Jericho system, you get Jericho silicon with 4 to 8 gig of HBM memory on every chip, right? So that's significantly more than Tomahawk class device that has 100 to 200 meg of memory, right? So you always need to look into total set of features you get on the chassis versus single piece of silicon before you decide which one is better for you. So it's not just number of ports and Radix. It's a very important point to consider.
Yeah, definitely. At least in terms, you mentioned really an interesting topic about deep buffers and some applications which are really sensitive. That also depends on what kind of flow control, congestion control, and error recovery you have, because especially not so recent implementation of RDMA, for example, they degraded really significantly to have packet loss. Some more recent implementations, they can do like selective retransmit and much more tolerant on that, but it really depends on workloads and applications. But for us, we really try to use shallow buffer switches where possible, and only if we must, we use deeper buffers, because thinking goes on like if there are large buffers and we use them, that means more latency. And if we don't use them, why paying for them? But of course, there are some applications which are really sensitive, or applications where it's better to have a little extra latency, but not dropping packets and so on.
Yeah, in one of the future episodes, we will talk about lossless networking and its smaller brother that is developed in ATF called DetNet, deterministic networking, and how it's implemented, amount of resiliency that's built into the switches, amount of not retransmission, but often packets are sent double to assure that one of them is actually arriving, right? So we'll discuss in more details in future podcasts, but building lossless networking is really interesting and quite complex technology.
This is it's been a fascinating discussion for me. I've been probably not participating in the discussion because I'm furiously writing notes here because I'm so interested in what you guys are talking about. But speaking of future episodes, we're kind of a little past our normal stopping time. Is this a good place to maybe wrap things up today and come back to it in 2 weeks?
Yeah, I would think so.
Yeah, that's good for me. And if you have like 2 minutes,
absolutely,
I want to like finish the discussion of switch Radix. Basically, I have a theory that why 128 Radix, if there are single interface, is probably what we are going to see for foreseeable future. It goes like that.
Sure.
One interface, we probably have 4 electric lanes inside it. 128 by 4 is 512. At current speeds, each lane is using differential pair in each direction. That means it's 4 traces per lane. And for 128 with 4 lanes, that means we are going to have 2K traces. And on modern chips, modern packaging, useful lanes like carrying actual signals are less than half. That means if we are going to have 2K traces for signals, it's probably 4K something pins on the package. And beyond 4K, 5K pins, the packaging becomes also becomes much more complex and more expensive, and really like physically large. So probably that's how many traces and lanes we are going to have for foreseeable future, because if we go to the next power of 2, that means 4K signal traces, about 8, 10K pins. The chip package, we're probably not going to see that, at least for next couple of years.
Okay.
I think it's been really great discussion, and actually very good segue into our discussions for next couple of podcasts.
Yeah.
There've been really a lot of information that should be really discussed in more depth. And if you've got any questions, please do send us questions. We are going to be here in 2 weeks. Dima is going to join us again. So please do let us know.
We have a lot of things to discuss.
Yeah, where to expand, and we would be happy to address any questions.
Dmitry, thank you so much for taking the time to join us this week, and we look forward to talking to you further and diving deeper into this in 2 weeks.
Thank you for inviting me. Definitely want to join more.
Thank you, and see you in 2 weeks. Thanks, everyone, for listening to us.
Thanks, everyone.